Hi, everybody. Thanks very much for joining us today. Welcome. And we're pleased to present our latest webinar, Accelerating Simulations Using JuliaSimCompiler. I'm Misha St. Amand. I'm the head of marketing here at JuliaHub, and I'm joined by today's presenters, Brad Carman and Yingbo Ma. Brad is the head of our consulting services group. He has over 2 decades of experience in model-based innovation and design, and he's an experienced user of Modeling Toolkit and JuliaSim. Yingbo is an engineering lead on the JuliaSim team and the lead developer of MTK. If you have any questions during the course of the webinar, please put them in the Q&A and we'll answer them as we go along. One question that's frequently asked right off, we will be sharing a recording of the webinar and any supporting materials with all the registered attendees over the next few days. So expect an email in a day or two with that information. But now I'll turn things over to Brad and Yingbo.
Thank you. So to get started, let us first talk about the Julia language and SciML. These are the foundations to establish so that what Yingbo is going to discuss next, the JuliaSimCompiler, makes a lot more sense. So first, probably most of you out there watching this know what Julia is and know why it's so good. But just in case you don't, or if you need a good explainer to bring to your team or to your manager to help convince them that Julia is the right tool to use for your team, I think this is a really good slide to kind of put it all on one page, why it's so powerful. So in doing coding work, when you're trying to just get something done using a computer language, programming language, there's basically two things that kind of create a bottleneck. There's the time that it takes the human to do the work, and then there's the time for the computer to do the work. And that's what this plot is kind of summarizing. On the x-axis, it shows compressed code size. Essentially, that's equating to how much time does it take a human to write the code to do the thing that you need it to do. And then on the y-axis, you have the execution time. That's how long does it take the computer to actually run that program and do something useful. And what you can see is if you're in the bottom left-hand corner, that is the optimal spot. That is where you're spending the least amount of time writing code and the least amount of time executing that code. And as you can see, this is where Julia sits. And that is what makes it such a powerful language. This plot, by the way, comes from a third party. This is not generated by Julia or JuliaHub. So it's a pretty trusted reference. And just a little bit more information about this, you'll see that there's 2 points. There's a square and a circle. So the square represents the least amount of code. This is just getting an algorithm down into code to execute what you want it to do. And the circle represents optimizing the code. So adding all the additional bits that would be necessary to make the program run as optimally as possible, like pre-allocating memory and stuff like that. So you can see languages like Perl, Ruby, Python. There's a big difference between just writing the algorithm to do what you want versus how much work it takes to get it to execute fast. There's a very big difference in both the amount of code that it takes and the performance difference. So just getting the algorithm down can be very slow in some languages. And this is another place that Julia really excels, is that the difference between just getting your work done and getting going and writing optimal code is very small. So you can get started and be very efficient right from the start. So there's a lot more about Julia that I could talk for a good hour about why it's such a great, powerful language. But I think this is a great place to start. Another reason why Julia is becoming more powerful is because of what I just discussed. It's becoming extremely popular. And that makes it even more popular because there are more tools and packages being written in Julia that allow you to do more useful things more quickly. And every year that gets better and better. And so one important example of that is the SciML organization, which is an example of that, right? So the SciML organization was formed because Julia is such a good language for just generic programming. It also means it's a great language for doing math, engineering, and science. And if you're doing math, engineering, and science, you're going to want to be able to solve equations. And so that's exactly where the SciML organization started, is that wouldn't it be nice if we have this really powerful language to have a nice, organized, very efficient set of solvers that we could use in that language? And so this list here is showing you the foundation of the SciML organization, the different types of solvers that exist, including optimization. And there's a lot more to be said about that, about how powerful they are. But this slide just gives a quick overview to show that when you combine the power of Julia with the work that has been done in the SciML organization, you end up with the state of the art. Julia is able to produce solving speeds that are beating that are winning, put it simply. So you can see on the screen we have a citation there. This is all open source work that can be vetted. But put simply, it is combining these two things together means that this is an extremely powerful tool for math, engineering, and science to get your work done. And one final point to that is that Julia is a full-featured programming language, which means that you don't just make a model and solve your set of equations and then you're done. You want to do useful work with that, right? And so it is a full-featured language. So you can build a model, you can build a simulation, and it doesn't end there. You can go ahead and insert it into your programs or into your processes or build algorithms around it. And one standard scenario with building a model is that you're probably going to want to run optimization and run many parallel runs of that simulation. And this is something where Julia also excels. So if you're going to be running lots of parallel simulations, you're going to want to do that on the GPU. And this slide is just showing that Julia also excels at that as well. So if we have this great foundation of the state-of-the-art solvers with the state-of-the-art programming language, wouldn't it be nice to have a tool that you can help you build models that you can use those solvers with? And that is where we get modeling toolkits. So that was also developed with the SciML organization. Now that they had these really strong set of solvers, it became clear that it would be great to have a tool that allowed you to build the functions that are needed to solve. Because it's not easy to build the function that you need to solve if you're trying to solve a set of equations and the corresponding Jacobian that you need. That's not something you want to do by hand on a regular basis, especially if you're an engineer who's doing a design exploration or a scientist who's doing an experimental exploration. You don't want to build these functions by hand. You want the computer to do that for you. And so that's what Modeling Toolkit is. It's a component-based modeling system, which is another word for that is acausal modeling. And acausal modeling, if you're not familiar with it, is a natural and analogous to real-life schematics. So what I show here, you have a spring mass damper system. This is exactly how you would probably see this show up in a physics textbook. Well, this is exactly how it looks in the modeling system. You have components that have the physics of each of that component defined, and you simply need to connect them together to create a system of equations. And this is a modeling system where you can, once you have the components, you don't even need to do any math at all anymore. The modeling toolkit will do all of that for you. And it's not tied to any specific domain. You could do mechanical problems, electrical problems, hydraulic, any domain is possible. And with a component-based system, it's very easy to edit and change the model. It's as simple as removing it. Like if you wanted to remove a spring, that's it. You just take it out, and now you have a system with just a damper mass and 2 dampers and spring, right? It's very simple. And being that modeling toolkit assembles the math for you, that makes this both efficient for the human time. It's just like this Julia slide that I showed at the beginning. It's very fast for a human to be able to do this work, but it's also fast for the computer, because in acausal modeling, the system of equations is not dictated by the modeler. The system of equations is taken by the system at the final step and optimized and put in such a way that it is going to be solved at the most efficient way for the computer. That is opposed to causal modeling, which I'll show in the next slide, is a very different situation. And one final point is that in a system like this, you can build libraries and subsystems and systems of systems. And this allows you to do the don't repeat yourself rule in programming, which is a principle that is best for working in teams and being as most efficient as possible. You can define one spring that lives in a library in one place, and you can reuse that throughout your model. That way, if at any point you want to make a more advanced spring, you update that in one place and your entire system gets updated. So it's a very powerful modeling tool. So as I said, let's contrast that with causal modeling. So causal modeling is a block diagram type modeling system. And in this type of system, which you have to do a lot of work to get your model into this type of system. So if you were to take an RLC circuit, for example, you need to figure out what the equations are and lay them out in a way such that you can connect the variables together. And you're basically dictating the flow of math when you do a causal modeling, block diagram type modeling. And that means that you've taken away the opportunity from the computer to optimize this set of equations. And another point is a block diagram is not really that useful for working together with other humans. If you were to show me this diagram, I would look at it and be like, all I see is math. I have no idea what this represents physically. And that is what is in great contrast with acausal modeling, where what you're laying out is a schematic that is very analogous to the real life problem. And so what I'm showing here is that to build the system of equations of an RL circuit in acausal modeling, it's simply an exercise of defining the components you want. So it's the RLC, right? Resistor, capacitor, inductor. And you just connect them together. And that's it. You're not writing equations. You're just connecting the nodes of each component together. And then you let modeling toolkit, you let the computer do the work for you of assembling all those equations. So I won't spend too much time on this, but just to show you how this magic happens, the way acausal modeling works is that each connection has a minimum of 2 variables defined, which we call an across variable and a through variable. And they simply have to follow the rules of defining the relationship between them. So for an electrical domain, for example, you have to define the energy dissipation and the flow. Energy dissipation is simply going to tell you what is the relationship between how voltage changes to the current that results. And the flow is just what is the linear relationship between the voltage potential and how much current you get. So this isn't not what you need to know, but this is just so that you understand how it kind of works under the hood, is that with each connection, we now know what the voltage and the current is at each one of those connections. And the system is going to ensure that those across variables are set equal. So when you connect a capacitor to a resistor, at that point, the system is going to say, okay, the voltage here should be equal. Or if it's a a mechanical problem, it's going to say, well, where these two meet, the mass and the damper, the velocity should be equal. And then the second rule is that the through variables should sum to zero. So that means at each of these points, if it's an electrical problem, the through variable's current. That means the current should sum to zero at this point. Mechanical, the force should sum to zero at this point. So that's it. Those are the rules of this acausal modeling system. And like I said, you don't have to do this work yourself, but it just does all that for you under the hood. At each point, it's going to assemble those equations and put together the problem for you. So a quick example, that electric circuit that I'm showing you, as I showed you, you can easily define it by defining the components, connecting them together. You assemble the system, and at this point here, when you assemble the system, this is when Modeling Toolkit figures out what all those equations are. So in this case, you're going to have 1, 2 connections. So that's going to be 4 equations. There's going to be an equation for the resistor, equation for the capacitor, equation for the ground. So it's going to have about 7 equations at this point. The next step is to run this through structural simplify. So this is a function provided by Modeling Toolkit that is going to, it's like having a bunch of mathematicians in a box. They're going to look at that set of equations and figure out the most optimal way to solve them. And it's going to do a process of tearing and simplification. And in this case, turns out that you can actually turn that problem into just one equation, which is written here. And then finally, you can take that simplified system, turn it into a problem which fits into those solvers that I was showing before. So the SciML solvers can now be used. And you didn't have to assemble the functions, assemble the Jacobian and all that stuff. You simply just need to assemble an ODE problem like this, and you can solve it. In this case, I'm not even specifying what solver I want. Differential equations, actually one of the features is it'll try to determine the best solver for you and automatically do that. But you can also choose from a very complete list of solvers and specify and fully configure them and solve it however you want. So hopefully that gives you a good idea of what Modeling Toolkit offers. So now let's expand on that. Going beyond Modeling Toolkit, we have something called JuliaSim, which is kind of the collection of all of the tools to build and simulate problems and then do lots of useful things with those simulations. So at the start, we have what I established, right? Our Julia and the SciML organization. That's the foundation for all of this. On top of that is the Modeling Toolkit tool to allow us to build problems and simulations. And Modeling Toolkit, as I discussed, enables the ability to have predefined libraries of components. So we have a Modeling Toolkit standard library, which has all your foundational physics, electrical, hydraulic, mechanical, magnetics, heat transfer, all of those, you know, college foundational physics. But JuliaHub is also building out a collection of libraries for niche, challenging areas. So we have HVAC, battery, and multi-body, which we're currently have now in our portfolio. And finally, with that, now that you have the ability to build these models, you'd like to actually do some very useful things with them. And so that's what JuliaSim offers, is this collection of tools or toolboxes, you could say, to do, as it says here, design, discover, calibrate, control, and surrogatize. And yeah, feel free to ask questions. We can expand on those things. But what we want to talk about today is this first bit about how we can run simulations faster. And one thing about acausal modeling, as I discussed, the structural simplify step is like having a bunch of mathematicians in a box that can optimize the problem mathematically. But we also need to consider, how do you optimize the problem for the computer itself, right? Because in the end, it's not going to be mathematicians sitting there actually computing, it's going to be the CPU. So we also have to consider, how is this going to get compiled into code that is most efficiently run on the computer? And that is where JuliaSimCompiler comes into play. And with that, I will hand it over to Yingbo to properly explain what JuliaSimCompiler is.
Hey, can you hear me?
Yes.
Oh. And can you see the slides?
Yes. But before we start, there was one question that just popped in, which is, I think, Brad, this is for you. Will the multi-body library and other libraries that you talked about be proprietary parts of JuliaSim or transfer to MTK?
Yes, they will be proprietary. My apologies for not making that fully clear, but the standard library is open source. The niche libraries are proprietary, part of licensed, JuliaSim licensed product.
Thanks, Brad. Thanks, Brad. Yingbo, back to you.
Yeah, so this is Yingbo, and I will talk about JuliaSimCompiler and its transformation process. So before we talked about the scaling property of JuliaSimCompiler, so if there is only one thing that you take away from my portion of the talk, is that it is, of course, the way to actually use JuliaSimCompiler. To use JuliaSimCompiler, you actually only need to add 2 lines on top of your existing MTK model. So in MTK, you simply call structural simplify on the constructed model to get a simplified system. In JuliaSimCompiler, first, you just need to load JuliaSimCompiler using syntax, and then just call IR system on the MTK system to convert it into a data structure that is within JuliaSimCompiler. And then everything else is going to be the same. So we are still going to call structural simplify, and and everything else would follow. You don't really need to change any other lines of code. So yeah, so you just need 2 lines to turn on a JuliaSimCompiler to get a huge scalability improvement. And as far as we know, this kind of scaling problem has not been solved in any acausal systems. So in short, MTK is an open source, openly available model platform, but with JuliaSimCompiler, you can even get the most. You can also have the most scalable platform as well. So to get scalability, let's first talk about loop rerolling. Loop rerolling is a pass that rerolls similar expressions back to one for loop to minimize compilation and to also minimize the runtime. So in here, for a simple example, we are going to use the ladder RC circuit. And to declare a ladder RC circuit, in MTK, you can use the @name syntax to declare all the repeated components. So in here, in particular, we are saying that we are declaring n registers that are exactly the same model and n capacitors that are the same model. This is a really important step in the front end because if we want to detect repetition later in the compilation pipeline, we have to solve an equivalent of subgraph isomorphism. But it is provable that subgraph isomorphism is actually NP complete hard. So to solve it optimally, it's gonna take ages. But then we don't actually, but if we don't drop the repetition information in the first place, we don't have to run the subgraph isomorphism problems over. So in here, yeah, it is important for MTK to capture this repetition information in the front end. And to do that, simply you just need to use this syntax. And later, if we expand all these equations out in MTK, it will look something like this. Note that the first equation and the fifth equation are basically the same equation, right? The only difference between the first equation and the fifth equation is that the first equation only refers to the first resistor, and the fifth equation only refers to the second resistor. And so the second equation and the sixth equation, the sixth equation are also in the same form, right? To capture this kind of repetition, in JuliaSimCompiler, we use variable classes and equation classes data structure to store it. In variable classes, it's simply it simply is an vector of vectors. So in the first variable class, there will be, for instance, register 1v and register 2v. Because they are essentially the same variable, right? They semantically basically mean the same thing. It's just that they appear in different instantiations, but they mean the same thing mathematically in the model. And the second variable class is going to be something like register 1 PV and register 2 PV, like this variable and this variable. And for equation classes, the first equation and the fifth equation are basically of the form of 0 equals to x minus the difference of y and z, right? And the second equation and the sixth equation are basically in the form of 0 equals to x plus y, right? So with all this information, the loop rerolling compiler transformation pass can reroll these simplified JuliaSimCompiler expressions down to a single for loop with a few scalar evaluations, of course, in the surrounding. So in this case, if n equals to 100, so if we have 100 registers and 100 capacitors, we got a loop that is 97 long. It is not exactly 100 because there are boundary conditions in the source term and in the sink term. But 97 is basically almost as good as you can get. And if we look at the content of the loop, this is equivalent with a matrix vector multiplication where the matrix is tridiagonal, right? So this is the best you can do actually for the ladder model. And when we apply the loop rerolling transformation pass on a more realistic real life example, for instance, on the battery model, we see a good scaling as well. So let me just try to explain why we really care about battery scaling. So as far as we know, there is not a single tool available to actually that can actually simulate the entire battery pack for electric vehicles. Electric vehicles tend to have thousands of smaller battery cells for in their battery pack. And if we don't apply looping, right, the compile time would actually blow up quadratically. So you can see that even for a few hundred battery cells, it takes more than 2 minutes already. And because it scales quadratically, it easily just the compile time easily can be on the order of a few days or even weeks. But if we apply looping, we can easily compile 5,000 lines, 5,000 battery cells in the battery pack, and it will still take only about 1 minute. And of course, to show that our transformation is valid, we plotted both solutions, both total voltage as a time series. So we can see that the solution given by the looped form and the scalar form coincide. And this model is specifically a single particle model for the lithium nickel manganese cobalt oxide battery cell. Okay. So that was, I'm seeing a question. The question is, the number of components for the as a parameter is kind of like a structural parameter, right? When you vary the number of components, you actually change the number of equations you have in the model, right? So when you change the number of components, you must recompile the model, right? And you need to recompile the model and then run it simulated again. You can't just only change the parameter, and so the compiler wouldn't figure out how to solve the system without recompilation, right? Because changing the number of equations is changing the system in a fundamental way. So the compiler must reanalyze everything. Okay. Yeah. Yeah. So that was about scaling of the compile time performance, right? Because the compilation speed scales quadratically without loop rerolling. So it is important to improve it's mostly important to improve the compile compile time. But for runtime, we also have another optimization called inline linear solver optimization in JuliaSimCompiler. So one common complaint for modeling toolkit is that for multi-body models, it almost always gives you more states than what you think would be physically necessary, right? For instance, the simplest multi-body model is a pendulum. And if you just use elementary physics knowledge, you know that a simple pendulum only has 2 degrees of freedom. You just need angular position and angular velocity to fully describe the model. But if you feed this pendulum written in polar coordinate to modeling toolkit, you will actually get 4 equations and 4 variables. In particular, you get 3 algebraic equations and 2 algebraic variables that are lambda and the angular acceleration. But fortunately, if you observe the nonlinear equations carefully, you can see that lambda and the angular acceleration are always linear in the algebraic equations. So you can insert a single linear solve call in the compound model to eliminate all these 2 algebraic equations, and then you'll get a single and then you'll get 2 equations only, which is the optimal number of states for the simple pendulum. And if we use JuliaSimCompiler to solve the simple pendulum problem, it can actually report that there is a 6x6 linear subsystem. The reason that we see a 6x6 linear subsystem is that instead of 2, like we saw before, is that we actually apply this transformation path before tearing. So, but after for tearing we actually interpret it as a block linear algebra algorithm. So in here, this 6x6 matrix is partitioned into 4 parts, where A11, the upper left corner matrix, the matrix in the upper left corner must be lower triangular. And in this case, it's actually simpler than lower triangular, right? It is just diagonal. So solving it is trivial. And solving the tearing problem on a blocked linear problem is just simply following the following procedure, where the tearing is just equivalent with solving the A11 submatrix. And again, because the submatrix is just a diagonal matrix of -1, it is extremely easy. And this linear subsystem is responsible in solving for the acceleration in the Cartesian coordinate, the lambda variable, and angular acceleration, right? And because of the block partitioning of the A matrix, it actually tells us that after tearing, if we don't have this linear solver optimization, we would be left with the lambda variable and the angular acceleration variable, which is what MTK does. But after applying the linear solver, we can eliminate the whole equation away and get a 2-degree freedom system. So here's a demo for a few multi-body problems that is solved using JuliaSimCompiler. On the left, this is a 6-degree freedom robotics example, and on the right, this is a 10 pendulum example. Actually, another important thing about inline linear solver is that for 3D multi-bodies, it uses 3x3 rotational matrices to represent orientation, right? If we don't fully eliminate all linear algebraic equations, some of the entries in the rotation matrices will actually remain as states of the DAE. And they will be really hard to initialize because it's hard to get intuitions about the individual entries of a rotational matrices, of rotation matrices, right? And if you initialize it wrong, the DAE consistent initialization algorithm would also fail. So without this optimization, these 3D multi-body problems cannot even be solved. And before going to the demo, I want to acknowledge Chris Arald for doing a lot of work on the loop code generation, and you can find him at Chris Arald in GitHub. And now let's go to the demo for the battery pack, for solving the battery pack model using JuliaSimCompiler. Let me know if you can see my terminal.
Yeah, it looks good, Yingbo.
Yeah. So while I'm talking over it, I'm just going to execute the code on the right, so that hopefully when I stop talking about it, it will also stop solving. It will also finish solving. So in here, first, we want to load JuliaSim library. And then in here, we are instantiating a 10x10 battery pack. So it is 10 battery cells connected in series, and we have 10 of them together connected in parallel. So together, this would be 100 battery cells. So in here, because we want to solve single particle model for the lithium nickel manganese cobalt oxide model, right? So in here we call SPM with the configuration of NMC for nickel manganese cobalt oxide. And because we want to simulate a battery pack, so the connection pattern is going to be a battery pack of 10 in series and 10 in parallel. And to use the JuliaSimCompiler backend, we just need to switch the backend to be ICIR. And it takes a loop, keyword argument. If we set loop to true, then it will apply the loop rerolling transformation. And if we set it to false, it will not do the loop rerolling transformation. So it's just going to be purely scalar. And for the sake of time, I'm disabling the temperature modeling and ICI degradation for the battery pack. And finally, I'm just solving it with the configuration of charging at a rate of 1C with the initial state of charge 0. And then I'm plotting both solutions, both total voltage. One is the loop configuration, the other is the scalar configuration. And finally, I'm benchmarking the right-hand side performance. Because applying the loop rerolling transformation path actually sometimes can give you a little bit of overhead, right? So it is only worth to do loop rerolling when you have a sufficiently big system. If the system is too big, running the loop rerolling transformation might actually hurt the runtime performance. Okay, so it finished running. And this is the plot that it generated. So we can see that loop and scalar coincide again, so the transformation is correct. And compile time-wise, the loop configuration only took about 18 seconds, and the scalar configuration took more than a minute. So that's a lot of speed up. Also remember that the scalar code compilation time scales quadratically, right? So when we are simulating a larger number than 100 battery cells, it's going to be a lot worse. And soon it will even become intractable to even compile such a big model. And runtime-wise, also remember the first one is the loop configuration. The second one is the scalar configuration. So the runtime-wise, this system is sufficiently big so that we actually get a runtime speed up for applying the loop rerolling transformation. And I see that we have 15 minutes still. I can take questions now, or I can show a little bit of what happens if we decrease the number of battery packs and see like maybe loop rerolling can introduce a small amount of runtime overhead.
Yeah, I think it'd be nice to see a bigger.
You want to see bigger or a smaller model?
Whichever you feel safest running.
We can try 15, but then
let's try 15.
Yeah, I feel like it will take a really long time for the scalar model to compile it.
Okay.
The loop one would probably only take still below half a minute, but the scalar one would probably take multiple minutes to even compile.
Will it print out the time when it finishes the loop compilation?
Yes. Yeah. So, because in here we are using the at-time macro in here.
Okay.
It will eagerly print out the time when it finishes when it finishes the execution. Okay, yeah, half a minute.
29 seconds.
So correct.
So that means it's going to take the non-looped version, like probably a good.
Even let's say that the non-loop version scales the same, which would not be, would actually scale worse, right? So in the best estimate, we can scale it. Let's say this number divided by this number multiplied by 30, right? So yeah, we will wait for about 2 minutes.
Okay.
But
well, we have one question while we wait those 2 minutes.
Yeah. What's the theory behind the looping process? That is really complicated. I feel like I can like give multiple hours of lectures about how the algorithm works. But in short, it runs the normal acausal compiler process. But then in the scheduling part, so when it actually rearranges all the equation expressions and make some of the equation expressions assignments, it tries to topologically sort all assignments in such a way that you can loop the most amount of code. Does that make sense? So this is kind of like a pretty tricky scheduling problem. And we don't guarantee that we actually solve it optimally. That's why sometimes running the loop rerolling pass actually gives you a little bit of overhead in runtime. But normally the overhead is so negligible that for larger models, the speed up that you get from having loops actually weighs more than the little overhead that you got, right? So in the above case, even you even get a runtime speed up, a really short one, but a really small one, but nonetheless it is a speed up. Well, I guess we have demonstrated the point that scalar will take a long time to compile. We can probably go on. It's still compiling. It will take a long time. Okay.
All right, very good. So we can switch back to me then. Let me share. So thank you, Yingbo, for that very impressive, very brilliant work that you've done there. Let's just wrap up with discussing a couple other points while we have everyone online. A couple upcoming webinars, which are very relevant to what we discussed here. We have an Introduction to Modeling Toolkit workshop that we're going to be doing in a couple weeks. So if you haven't used Modeling Toolkit and you'd like to get started with it, this is a hands-on training. It'll be perfect for you to learn all about what we discussed earlier. And as Yingbo is demonstrating the JuliaSim batteries, we'll have another webinar in the, I believe it was January or February, where we'll give a demonstration of that in detail. And also it looks like we have one coming up next week about functional mockup units, which are essentially being able to take your modeling toolkit models and compile them to be deployed in other modeling tools. And one other final point is that we now have a consulting arm of JuliaHub, which means that we can help you. If you've watched this webinar and you think, wow, that's fantastic, but there's no way we're going to be able to get up to speed with all this stuff and actually make use of it in a reasonable amount of time, well, we have a team here that can help you get started and hit the ground running. So if any of these tools look like something that can help you get your work done, then please reach out to me and we can help. And with that, we have a little bit more time for any additional questions. Otherwise, feel free to reach out to us if something comes up in the future.
Okay, Brad, I have a question. If I want to use JuliaSimCompiler, do I need to change anything in my model first? Like registered functions, do they still work?
Yeah, Yingbo, that's a good question for you. I think in general, the answer is no.
Yeah, generally, yeah, if you are using registered functions, it will be harder to get it just work. I think it might still work if it doesn't require, if the model is not high index, it might just work, but I wouldn't count on it. I wouldn't promise that it will just work. Yeah, in some non-edge cases, it should work, but in some edge cases that you might need to do some additional work to tell how to take derivatives of the functions that you registered to JuliaSimCompiler.
Hey, I think that.
Sorry, I was just going to say, and I think one final point is if you're wondering if JuliaSimCompiler is right for you, I just wanted to, in case it wasn't obvious, I think Yingbo did a good job of demonstrating that, is if you're attempting to solve a problem that does not want to even compile, then you know that there is a tool there that can help you. You need to use JuliaSimCompiler to get that to be sped up. So
yeah, by the way, the 15 by 15 battery cell model finished. The scalar version took about 200 seconds.
200 seconds, okay.
30 seconds.
Okay, very good. So if you're waiting 200 seconds for something that should take a few seconds, then you know JuliaSimCompiler is what you need.
Okay, I think
Oh, there's another question.
So yes, does the loop rolling method also work with FMUs with lots of states, like 3000 states?
No, not quite. This only works with models that can be represented inside JuliaSimCompiler, right? Well, you can't really transform anything in FMU because it's already compiled. Also, I mean, like if you have MU, right, you already have it compiled, so you wouldn't get that scaling problem anyway.
Okay. Well, we are close on time, so I'm going to thank you, Brad. Thank you, Yingbo. And thanks to all of you who joined us today. As I said earlier, we'll send a follow-up email that will include a link to a recording of the webinar, and you can always reach out to us with additional questions. As Brad mentioned, we have a few upcoming webinars next week, one on MTK, one on FMUs, as well as we'll be unveiling our January webinars, including one on batteries in a week or two. So keep your eyes out. Visit our website if you want to register for those, particularly for the MTK workshop next week. So thank you, everybody, for joining us. Thank you, Brad. Thank you, Yingbo.
Bye.
Bye-bye.